Okay, so today's question is Josephus problem part two. So consider a game where there are n children, so it's the same as before in a circle. During the game, repeatedly k children are skipped and one child is removed from the circle. In which order will the children be removed? So basically, it's still the same problem as yesterday, except the two got changed to k. So then we're not skipping every one, but every k children. But obviously now the approach has to change because if we were to DQ then NQ K times and we see K can be up to 10 to the 9, we're gonna definitely exceed the time limit using a cube like approach. So an alternative to that is actually using a different data structure. And here I learned this data structure just today by doing this question. So essentially what we're going to use is a order statistic tree. This tree is basically implemented using a red-black tree, and then on top of that, we just kind of make sure that we have the indexes based on the order statistics. So that's kind of what we have. And I'll kind of walk through the code to kind of explain what we have. So in the first part, we just have include IO stream. And then specific to this question, because we're using PBDS, which stands for policy-based data structure, we kind of have to include these two extensions. One of them is called a container, and the other is called the tree policy. And then as usual, we have our using namespace std. And then because we're using PBDS, there's something called GNU, and then it would be kind of annoying to write it every time. So we kind of just define using namespace this thing to save some writing of the code later. Next, we define our type def of our tree, which is our key is an integer. Our value we just kind of don't care about it, so we kind of set it as no type. And then our compare our our comparison would be just less of the int. Basically, our tree is in sorted in ascending order. And then we have RB tree tag, which basically specifies that we want to make this tree a red-black tree, technically. And then the last one that we care about is the tree order statistics node update. So this one is just basically we want to update it based on the order statistic of the tree. And then other than that, we're gonna call it order set. So in our main, after defining this, we're gonna just like get the input so that's fa and output so that's faster with our classic iOS-based Synquist Studio and cin.tai. Next, what we have is our n and a k, and we input this. Pretty straightforward. And then we set our order set of children. So inside here, what we're going to do is from 1 all the way to n, we're going to insert the numbers into the tree, and it's going to be sorted. Next, what we have is our current position. Our current position we're going to set to be 0 because we're going to start there, right? And now while we're gonna continue looping until we eliminate every children until there's only one, um remainder is greater than 0. So we're done down to the last one, and then we remove that when we're done. And we're just gonna do a for loop, and every time we're gonna remainder will be minus minus. And in our loop, we're going to do current position is equal to current position plus k modulo remainder. So basically, in other words, we just directly find the position that we're interested in the next location that we're trying to kind of print out, right? So rather than just like having to do 1, 1, 1, 1, 1, we straight jump to that point because we know that it's k positions away and we want to modulo it by the remainder of what that is. And then we want to find what that value is. So we're just going to call an iterator. We'll just say auto iterator is equal to children dot, and then we use dot find by order, and then the current position. And then we get its value by just using this sign in front of the iterator, and we would get it. And then we just print it out, which is that child, like, it's their turn, and then we make sure that we remove it. And then because we implemented it using a um, red-black tree that's balanced, and it's also sorted based on like the ascending order and order statistics, it should be updated to that. So then every time we're in the right position, and then um, K and position would be updated based on what we need. So that every time we can get the chart we need. So then we kind of just directly, precisely jump to where we are. And the reason why we're using this order statistic tree is because it's kind of like we can get it to log in every time. Every time we're searching something, we only need to do log in because it's balanced. It's like a binary search tree. So that's why it's really efficient to do so. And because we can manage each one in log in, so then our algo would just be an in log in, and it would be slightly less than that because in is decreasing as we go down the for loop. So technically, our worst case scenario is O in log in. So it's pretty good. And then in the end, we just output um, the last line and then return zero, which is pretty straightforward. I think the major thing that I learned from this question was how to use the extension and then the PBDS to actually implement the order statistic tree. Other than that, the logic is relatively straightforward, I'd say. And the additional thing is that on a Mac, you don't have the GCC compiler, so you kind of have to download that and then compile yours. When you compile it, you kind of have to kind of work around that. So that's something to watch out for if you're a Mac user. Okay, cool. That's it.